Okay, so let's take a look at section 2.3. So what we're going to do today is we're going to talk about separating mixtures, and we're actually going to separate a couple mixtures in a couple labs after this. So let's start by talking about physical separations. If I'm not using a chemical reaction to separate something, like to separate a compound into its elements, then I am doing something called a physical separation. There are a ton of different physical separation techniques. For example, some of them would be centrifuging, which is where you spin things and you separate them based upon density. Like if you're trying to separate the components of blood, this is what you would do. Chromatography is what we will do today. There are a lot of different types of chromatography. The most common one that we will do is paper chromatography. And then you can recrystallize things by evaporating water from a salt mixture, for example. Decanting is where you pour off a liquid and leave a solid behind. Density separation is just like centrifuging. Distillation is where you separate things based upon boiling points. So you could heat like cherry soda and separate the components by the different boiling points. Electrophoresis is something that if you're going to go work in like a biochem lab or a cancer lab, you will probably use that to separate components like different proteins and stuff like that in a gel. Evaporation, extraction, and the list just goes on and on and on, okay? Now, physical separations can either be one of two things. They can be mechanical or they can be non-mechanical. So non-mechanical means I'm not going to be using like gravity or motion to sort things out, okay? So things like picking things out or filtering or shaking things would be mechanical examples. If I use electricity or heat, those would be non-mechanical, okay? And let's start by talking about density separations first. Density separations will have mixtures that are made of things with different densities. So that means when something falls or sinks to the bottom, that would be the sediment. So if I shake up sand in water, the sand will obviously settle to the bottom eventually. So the sand would be sedimenting because it would fall to the bottom of the liquid. But we can also use the word sediment as a noun. So the sand would also be a sediment because it is the matter that is sinking to the bottom of the liquid. Okay, let's take a look at the next page. They talk about some physics and forces in this. I'm going to go just gloss on over that. We're not going to have anything to do with that. I'll let you guys do that when you go to physics. But we're going to talk about decanting and filtrating because those are important in chemistry. So these are still relevant in terms of using density to separate things. But decanting is where you basically have a solid in with some liquid, and the solid has settled or sedimented to the bottom of that liquid, and you're going to carefully pour the liquid off and leave the sediment or the solid behind in the original container. So what does this look like? Well, here on the left-hand side is an example of decanting. So here would be my solid at the bottom of my original container, and then here is my liquid that I'm carefully pouring off. What they often do is they guide the liquid along a glass stir rod into another container. And I actually have videos, little teeny tiny video clips available for all of these different types of separation methods on Canvas within chapter 2, okay? Okay, let's talk about filtration. So I could also get rid of a solid that is mixed in with a liquid by filtrating it. So what happens here is you typically have a funnel with a piece of filter paper inside of it. Okay, the filter paper has pores in it, and we can use filter paper with different pore sizes. And what happens is the liquid will go through those pores into a different container. Now, the liquid that goes through is called the filtrate, and then the residue would be the solid that you're collecting on the filter paper. Okay, and what we typically do here is we take that filter paper that is wet with the solid on it, and then we put it into a watch glass and we let it dry. Sometimes in an oven, sometimes I let it just dry outside because it's so hot. Okay, all right, let's talk about centrifuging. Centrifuging is where you spin samples at a really high speed, and it separates things based upon density. So here you can see that these little teeny tiny vials contain mixtures, and you always balance out the components inside so it doesn't like fall off the bench and while it's spinning. And then as it spins, you would see different components separate based upon density. So the components that have the larger density, so they would be at the bottom. So if I've got something like this, a sample, and this is substance 1 and this is substance 2 in my mixture, this would have the lower density, and this substance would have the higher density. Okay. Let's turn to the next page and let's talk about chromatography. So this is what I'm going to mostly spend the next few minutes talking about. Chromatography is, if you're going to go on and take AP Chemistry, you will likely have a question about chromatography on the AP exam, and you're expected to know how to set up a paper chromatography or to sort of like analyze some sort of method that uses chromatography. So let's look right here. Typically, when we're using chromatography, we do a simple method where we have a piece of paper. It's kind of thick like construction paper, and we usually put mixtures of like different food dyes on it, and we separate the mixture, the colors that are in the dye, we separate them on the paper. Okay, so what happens is we separate mixtures that are in a solution, or the components of a solution, by flowing a liquid through them. Sometimes we flow a gas through them, but we will flow a liquid through them. And they allow the components in the mixture to separate based upon how well they're attracted to that liquid. So basically, if they're polar or non-polar. And they're traveling through a stationary phase. So let me explain what this means. So you've got a piece of paper, and this piece of paper is a special type of chromatography paper, and they often call the paper the stationary phase because it's not moving. Okay, and then what we do is we put a little pencil mark across like a few centimeters up from the bottom of that piece of paper, and then we will sometimes label with an X where we're going to put our sample. Okay, you always want to use pencil rather than pen because pen could smear, whereas graphite and the pencils do not. Then let's say we're going to separate blue food dye. So you would put a little tiny sample of that blue food dye right on that X so you know where it's beginning. And then what happens is you would put this piece of paper into a beaker, and then when it's in the beaker will have a little bit of solvent. The type of solvent that you use will influence the ability of that food dye to separate as the solvent travels past it. So the solvent is going to travel up the paper. Okay, and usually it can happen very quickly depending upon the type of solvent that it is. And it travels through the little holes that are in the paper through something called capillary action. And what happens is you may see different colors separate. So you're going to see this blue food dye travel either quickly or not so quickly with the solvent as it travels up. Now the solvent is called the mobile phase because it moves up the paper. Okay, the food dyes may be made of more than one color. So, and I'm just giving you an example here. Let's say I have two different colors appear on my paper. Okay, they will ask you questions about the different colors. The questions may be related to their polarity or how quickly they travel, or how much they are attracted to the mobile phase. So in this case, what I would say is the yellow would be more attracted to the solvent or the mobile phase because it travels further up the paper. Does that make sense? As opposed to the blue is staying more towards the bottom. So if your solvent was polar, like let's say your solvent was water, and then they'll often add a little bit of salt to allow substances that are polar to travel faster up with it. So if your solvent is water, then I would say that this would be more polar, this color in particular, and then this color would be less polar based upon where they traveled on the paper, okay? If I had a non-polar solvent, then the yellow would be more non-polar than the blue. Does that make sense? Okay, so whatever is like attracts like. So that's sort of the explanation that you would use here. Now, can I move this down a little bit? Okay. There are a lot of different forms of chromatography. Gas chromatography, column, thin layer chromatography, which is often abbreviated as TLC, and then paper chromatography. I'm just mentioning that because if you move on to AP Chem, you may read about that as well. Let's go down a little bit more. And this entire thing is actually once the separation occurs and your solvent has moved up to about here, a few centimeters from the top, this is called a chromatogram. And that's just what we call the entire apparatus. Okay, so this entire thing. Okay, now, at the bottom of this page, they give you a picture of a developed chromatogram, okay? So if we come down here, you'll notice that they've got a solvent. This solvent cannot go above the mark of where you put your mixture because it would spread the mixture and make it impossible for you to obtain data. So just make sure of that. So over here, you're going to notice that we actually have 3 different color fronts. So they will often refer to these as fronts. So I'm just going to make a note that we have 3 different fronts. 1, 2, and 3. Okay. And we may be asked to calculate something called a retention factor, which they talk about on the next page. So a retention factor is abbreviated with RF, okay? Depending upon what lab you're reading or what resource, this is also known as the ratio of fronts. It's the same thing. What you're going to do here is you're going to calculate in centimeters the distance that color front traveled. If you only have one color, you would have one RF value. But if you have multiple colors, you would have that many RF values. So here you would have 3 RF values because there are 3 color fronts. So keep this in mind when you go to do this lab. Okay, so I'm just going to calculate one of them for you. If I'm calculating this RF value for this yellow color front here, you would measure from the pencil line up to like the thickest region of that color front. Now, the sig figs here are wrong. Technically, this would be 2.70, right? Because your division size is 0.1. So this would be 2.70 centimeters. So the distance that the color travels divided by the distance that the solvent travels, which is from the pencil line to wherever the top of that solvent ran to, which in this case is 5.40 centimeters. And then what will happen is centimeters will cancel, and then you will have that value. So this is going to be 0.500 because I need 3 sig figs. Okay? Okay. After you guys have let the solvent run up, what you typically do is you draw a pencil line across the piece of paper as fast as you can because that solvent will keep on running because it's wet. Okay? So, and you want to take a picture of it. I would put like a centimeter ruler next to it. I would put the centimeter ruler starting here with like the 0. And then take a picture of it before it runs and then use that to do all your calculations.